And the first group of applications were driven by the economic advantages that a real-time or dynamic underkeel clearance system offers in terms of being able to load bulk export ships deeper than can be safely loaded under static rules. So the economic driver was very much the reason why this whole technology started in the early 90s, and the first group of Australian ports there on the left-hand side of the timeline were all applications, except for Fremantle, which was an import of crude oil from the Middle East. The others were all export-driven. And then we moved across the Tasman in the middle of that timeline to New Zealand, and the first two ports there, Taranaki and Napier, were again export bulk primarily, although Napier did have containers. In 2003 we had the first safety-driven installation, which was at Whangarei in New Zealand for the port of Marsden Point, where there were two groundings that happened in the channel in 2003 because the pilots did not judge correctly the amount of underkeel clearance needed in the swells operating at particular times of the transits. So as a result of that, our system was installed at the port, and that was the quickest installation we had up to that time, or in fact we've ever had, I think. It was driven very much by the safety and the threat of closing down New Zealand's only oil refinery if the stringent static rules which were then applied were to be continued. In recent years we've moved a little further afield or abroad to Europe. We have installation in Lisbon now, and also applications for container vessels. Lisbon and Bremerhaven in Germany particularly, container vessels. In Lisbon you have again very big swells at the entrance, so the difficulty of pilots being able to estimate how much underkeel clearance is safely needed for their transit. And in Melbourne also container vessels, and in fact the largest container vessel, I've been told this morning, largest container vessel by far to visit Australia is coming in this weekend, so using our system. So we'll assume that we have our accident-free record will continue to hold as that event unfolds. But we'll certainly be watching it very closely. With the products that have developed from the earliest DOS-based version of version 1 of DUKC for Haypoint, written in Fortran, that has all changed now to much more sophisticated IT and software and communication devices. The early developments were for desktops, run on desktops in ports centres where the environmental data of tides, waves and currents were fed in, and the system did the number crunching to give the answers, and the pilots were given pieces of paper to take on board. The technology's now moved where it's possible to transmit this information onto portable pilot units carried by pilots and into VTS centres, as shown in the bottom right-hand corner of that slide. So the latest release of DUKC Series 5 is geared to providing this information to the users at the point where it's needed, also to integrate the information in with other applications within ports and waterway operations. There are many organisations which need access to information. For example, if a ship is delayed because of a tidal window changing with environmental conditions, then tug operators need to have that information. So these systems are now being integrated into port information systems so that all users can be updated of any changes which have been caused by restrictions on underkeel clearance. The solution is to provide the centralised information and control, and then disseminate that information by allowing flexible access, and the web is now a medium which allows that to be accessed by a large number of different users remote from the site. So this of course also allows the appropriate authorities to control access to the systems at various levels, so that users at whatever level they've been authorised, can access various amounts of information. And it reduces the need for duplication of systems. Also, the systems are scalable in that they can grow and evolve as the organisation and environment changes. So it can grow. An example of that is Port Hedland, which started in a system in 1995. At that time, the export of iron ore, which is its primary export, amounted to 70 million tonnes per year. That is now 180 million tonnes a year and projected to grow to 350 million tonnes a year over the next 3 years, all driven by the demand from our friends in China. Enormous growth in these ports. And so the systems are geared to be able to grow with that growth, and now instead of the problem of maximising the output from one ship by sailing on the high water, they're going to have to get the maximum throughput from 5 ships, which becomes an optimisation problem. So every high water in the future there'll be up to 5 ships sailing down the same channel, one-way channel, and the objective then is to maximise the total throughput of iron ore from the port for each high water. And these are large sums of money involved. Every centimetre is another 150, every centimetre of draft that is obtained is another 150 tonnes on the very largest vessels, and so another 50 centimetres to a metre means another 6,000 to 12,000 extra tonnes can be carried. So that's where the economic drivers come from, but safety is always a major concern, and our systems have always been put in as a basis as an aid to navigation and to reduce the risks of grounding by providing accurate and up-to-date information on the underkill clearance requirements. The systems are obviously configured to the various needs of the particular users in each port, and as every port is different, those needs change, and the graphical interfaces are designed, customised for each port in which we have applications. The overall design of the Series 5 architecture, I won't go through here, that's in the paper, and again, if you have any questions, you'd be very welcome to come and see us in the hall. I want to quickly go through two case studies, Torres Strait and the Port of Melbourne. Torres Strait case study that we've been concerned with over the last 2 years has been optimisation of the export of bauxite from Weipa in North Queensland through the Torres Strait to Gladstone, where the refinery is located down the eastern part of Queensland. And that is 3 UKC choke points or control points or bottlenecks, 1 getting out of Weipa, 2 going through Torres Strait, and a paper on Friday by Mahesh will give you a broad framework of the UKC management system proposed by AMSA for that. And the 3rd will be coming into Gladstone. A DUKC system was installed at Weipa 2 years ago, and that is well bedded down now, and ships are able to exceed the 12.2 metre limit when they're going to Europe, but the 12.2 metre limit at Torres Strait, of course, is still a constraint, and it's hoped that eventually a UKC system will allow that constraint to be made more flexible, because there is, during the summer months, 70 centimetres more water in Torres Strait than there is during the winter months. So there is the opportunity with a dynamic system to be able to take advantage of those economies. But as Mahesh will probably explain to you, Torres Strait, and very similar to the Chilean example which we saw before, I was very interested to see that through the straits, because again you've got narrow passages, in this case through coral reefs, very high currents up to 6 knots, and as all mariners know, squat is really affected by speed through the water, so very important to be able to predict what those current speeds are. You can't just look out the window and get an accurate assessment. So models are needed not only for the ship dynamics but also for the hydrodynamics, from sensors that measure the water levels in real time to feed that information into hydrodynamic models